We'll start by going through some basic SPR theory. Surface plasmon resonance, or SPR, is a label-free interaction analysis technique, which is great for us because it means that we don't need to spend any time or money labeling our samples with radioactive or fluorescent probes. The diagram here shows the basic assay format that's used in SPR. So this consists of a gold sensor, which will be performing all of the detection for us. Next, we'll need to immobilize one of the binding partners to the sensor surface, while the other binding partner is going to be free-flowing in solution above. Now, throughout all SPR literature, specific terminology is used to distinguish between the two binding partners. The binding partner that's immobilized onto the sensor surface will be referred to as the ligand, or sometimes pronounced the ligand, while the free-flowing binding partner will always be referred to as the analyte. Now, the great thing with SPR is that both of these binding partners can be a variety of different biomolecules, and this can range from proteins to peptides, to viruses, down to DNA and RNA, and small molecules or lipids. SPR analysis is a real-time technique, which allows us to get data on the full binding kinetics of our interaction in real time. As you probably are aware, the OpenSPR is a little bit different than traditional SPR instruments, as we're employing the use of a new sensor technology. Traditional SPR sensors consist of a thin film of gold on a glass substrate. Now, because this film of gold is so thin, it exhibits surface plasmon resonance, which means that the properties of the gold film are able to detect changes in the refractive index. Now, this change in refractive index is detected by measuring the reflectance angle. So, as a biomolecule comes into contact and binds to the sensor, it will change the refractive index, which will be reflected in a change in the reflectance angle, and then this allows us to measure the binding event. Now, with our sensors at Nicoya, instead of using the flat, thin film of gold, we have a nanostructured gold surface. Now, by employing the use of these gold nanoparticles, we're taking advantage of what's called localized surface plasmon resonance, or LSPR. It's the same sensing effect as traditional sensors. We are still monitoring changes in refractive index, but now our sensing field is localized much closer to the sensor surface. And this is actually quite advantageous for looking at binding interactions, because we only care about what is binding close to the sensor surface, and we don't want to detect our molecules that are free-flowing in solution over top. Now, with this new sensor technology, we are able to greatly simplify the optical detection technique that's required to monitor the binding interactions on the sensor. And this is why our instrument is much lower in cost and much smaller in size compared to traditional SPR instruments. So we employ the use of a very simple and robust transmission optical detection technique. We take an LED light source, shine it directly through the sensor chip, and right into the optical detector. We are no longer using the complex reflectance angle detection technique of traditional SPR instruments. Now, the property of our sensor that we are going to be monitoring is called the absorbance or resonance peak. So our nanostructured gold is going to absorb light, which creates this absorbance peak. And the center position of this peak is going to shift as binding events, or changes in refractive index, occur. And this new peak position will now give us our sensor response. Again, we're measuring the exact same properties as traditional SPR, but we're just measuring them in a slightly different way. Now, an entire SPR experiment will take place within the SPR instrument itself, and each stage can be characterized in real time. For an experiment, there are 3 general stages that occur. First, you will start with a bare sensor surface, and this is often pre-functionalized to a specific chemistry. Next, you will then need to immobilize one of your binding partners, which is the ligand, onto the sensor surface. And this will be associated with an increase in response followed by a new baseline. And then after that, you will be introducing your second binding partner, the analyte, over the ligand at several different concentrations. and this will be associated with different response changes for each analyte injection. Now, I will be reviewing each of these steps with you in detail throughout this rest of this section. Determining binding kinetics is one of the most common applications of SPR. However, you can also look for higher level information such as a simple yes or no binding or the equilibrium constants. But binding kinetics can give you much more detailed information about the molecules and systems that you are studying. Now, to get these accurate binding kinetics, as you introduce your analyte over the ligand at different concentrations, you will collect what are called binding curves. Now, a binding curve consists of an association phase and a dissociation phase. The association phase is when the analyte sample is passing over the sensor, and then you will see an increase in the sensor signal, which corresponds to the binding events with the ligand. Now, the dissociation phase is when there is no analyte present over the sensor, and the signal begins to decrease as the analyte dissociates from the ligand. Now, before you start to collect your next analyte binding curve, unless you have an interaction with a really high off rate, you will need a regeneration solution to remove the analyte from your ligand so that you can ensure you have the same number of ligand binding sites available for each analyte injection. Now, during this regeneration, the analyte is removed and your signal should return to the same baseline as before the analyte was injected. Now, we will discuss this regeneration in more detail later on in this section. Now, to obtain accurate binding kinetics, this process of your association and dissociation followed by regeneration should be repeated with 3 to 5 different analyte concentrations. Now, the association phase will give us data on both the on and off rate, while the dissociation phase will give us data on the off rate only. And then these on and off rates will then be used to calculate your final KD value. Now, this value is often referred to as the binding affinity constant, but the true technical term is the equilibrium dissociation constant. But just keep in mind that these are often used interchangeably. And a good thing to note is that when you are referring to the affinity or strength of an interaction, it is proportional to 1 over KD. So this means that a smaller KD is associated with a higher affinity. Now, this concludes our brief overview of the SPR basics. If this was all new to you, I do recommend some additional background readings into the subject as it will help you be able to understand and interpret your experiments.